All right, so we are jumping into section 2.2 right now, and 2.2 is an extremely important section because we learn about one of the biggest concepts of all of AP statistics, which is the normal distribution. Now, you guys would have already had a little bit of experience with the normal distribution from Algebra 2, where I had to teach you guys just the basics of the percentages that go in each section, and we will review that again in this video before we jump from there into more complicated stuff related to the normal distribution. We use this information the whole rest of the class in AP Statistics. We're going to see it in chapters 6, 7, 8, 9, 10. The whole second semester really takes this stuff and builds on it. So this ends up being one of kids' preferred chapters, I would say, because once you learn how to do these problems, they're really not bad, but they are extremely important for us moving forward. So, before we get to the actual normal distribution, I need to introduce a general vocab term called a density curve. And we've learned already how to graph quantitative data with things like dot plots over here and with histograms over here. The thing about dot plots and histograms and other sorts of graphs is they take a little bit of time to draw if you want them to be detailed. Sometimes we don't care so much about the exact points, we just want a basic sense of the shape of the graph. So rather than draw this dot plot like you guys see right here, we might essentially trace over the dot plot with some sort of a smooth curve to represent the data set. So I would not need the dots anymore, but I'd instead have this blue bimodal picture right here with the two different peaks. And this would be able to represent pretty well what's going on in the dot plot. On the second picture here, you can see they already drew a density curve in red. So just to highlight it a little bit for you guys, we'd be looking at a density curve like this to represent our histogram. So if you're not so concerned with the individual data points, but you're more just concerned about the overall shape, or if you're just doing a hypothetical where you're talking about a population that you haven't collected data on, but you think you know the shape of, that's when we use a density curve. So what does a density curve do? It traces over a graph of quantitative data and smooths it out to give us an idea about the population. So the whole idea with the density curve is you kind of make a quick, just smooth picture of what the population basically looks like. So we can use that theoretical graph to analyze the situation in more depth. There are a few rules that go along with density curves. The two biggest ones are, first of all, the graph is always above the axis. I'm going to say technically it's like an x-axis. In other words, you can't have any negatives. So if I was going to take one of these pictures right here, I could not have it where like the graph dips down over here before coming back up, because what that would mean, this is my frequency right here on the y, this would be like having a negative frequency. So that's no good. You can't have any negative portions on your density curve. And the most important rule of a density curve is that the total area underneath the curve, so total area under the curve, is always 1. Okay, so the total area under the curve is always equal to 1. So if I look at my blue curve right over here, for example, the total area underneath this curve is equal to 1. Why? Why make it 1? What sense does that make? Well, if I break this picture right down the middle, or that was supposed to be down the middle, and I care about just this part of the picture right here, the area of that part of the picture is a 0.5, assuming it's symmetric here. 0.5 is 50%. So if you look at your full area as 1, whatever decimal you get for your portion of it, like if I tack down like this part right here too, Now maybe I'm in like the 0.6 or 0.7 range. That tells me that area is the percent of the data points that have values in that range. So 70% of the people in the graph live in this red area right here. Okay, so the area corresponds to the percent of the picture, which is why we always make it out of 1. So let's move on. Now that we understand the basics of a density curve right here, some of this on this slide right here is review. Where do you find the mean, median, mode on a density curve? So the mean, remember from last chapter, the mean from last chapter is going to be the balance points. So I talked in chapter 1 about where I would put my finger to be able to balance that picture. On my first picture, it'd be right here in the middle. On the second picture, evidently, it'd be like right here where it wouldn't tip over. The median is your equal area points. And in a symmetric graph, those will be the same thing. The balance and the equal area are both in the middle, like you see right here. And remember, if you have a skewed distribution, the mean gets pulled towards the tail, towards the outliers right there. So the mean will be closer to the tail than the median is. The mode, we don't really talk about the mode a lot in AP statistics because it's not that useful. But the mode is going to basically be your peak. The most common point is the tallest point, like there or like there. So generally, again, just to restate what it says right here, it's basically when you make a density curve, you're making an idealized or like a hypothetical version of what you think the population looks like. And because we're talking about the population, it's assumed you mean population, not sample. When you make a density curve, we use Greek letters, our population symbols, for doing so. So the mean is going to be with our mu symbol that we've seen before. And our standard deviation is going to be sigma. So you will see these two symbols a lot when it comes to density curves, particularly with the normal distribution that we're about to learn. So before we get on with the actual normal distribution right here, I want to do a quick mini sidebar and talk about this guy over here. This is actually an old German Deutschmark, which is like their currency before they switched over to the euro. And in the US, we have presidents and stuff like that on our money, but they have mathematicians and all sorts of famous people on their money, or they used to before they switched over. And if you notice here in the background, they actually have a normal distribution on their money, which is pretty exciting. So this guy's name is Carl Friedrich Gauss, G-A-U-S-S, and he is like one of the most brilliant people of all time with regards to math, science, etc. Kind of my role model in terms of just really awesome mathematicians. He actually invented so much stuff and figured out so much stuff within the context of statistics, regular like algebra, calculus, astronomy, physics, that they basically stopped naming things after him because he had just invented so many different things. So really impressive guy, and he used to be on their money. So anyway, the normal distribution, I'm assuming that because you had me for Algebra 2, you're at least a little like you've seen this before, because we've had to cover it for the EOC in Algebra 2. But the normal distribution is a bell-shaped graph like you see here or like you see here. And when you draw your bell-shaped graph, never, ever, ever make like a parabola hill type shape. That's a really bad thing when you draw a normal distribution. It's like offensive. It hurts my soul when I see people draw normal curves like this. They do have what's called an inflection point right there, which is where you switch from opening upwards, concave up, to concave down. So when you draw one of these things, make sure they have their nice inflection points and they're not just simple parabolas. So according to the CDC in the US, the height of 12-year-old males is approximately normally distributed with a mean height of 149 and a standard deviation of 9. We're going to sketch this distribution, label the mean, and then some extra points as well. So the first thing I'm going to do, a normal graph is used for quantitative data. So we're still graphing them on a number line, very much like we would do in Algebra 2 or with other sorts of graphs we've talked about so far. And when you draw a normal distribution, I find it easiest to start on the ends. So I'm going to start right here. That was not the best. Oh, that's so sad. I'm going to do that again. So we're going to draw ourselves a nice looking normal distribution. This is just a disaster. It's hard to draw straight lines with this. All right, so there's my number line. And then we are going to draw ourselves a nice looking normal distribution. When you draw the normal distribution, the idea is that values in the middle are very popular. I don't know what 149, like that doesn't make as much sense to me because it's in centimeters and I'm in the US and I need like inches and feet and stuff like that. So I'm going to use adult males as an example here. I think I did this in Algebra 2 as well. If you are an adult male in the US, the average height is somewhere around 5'11 or 6 feet. So here's 5'11 or 6 feet. Lots of people have that height. So the graph, the frequency is quite high over there. If you go to like 6, 6'1, 6'2, still pretty popular. Same with 5'10, 5'9, 5'8, 5'7. Those are popular values. But by the time you get to like 7 feet tall, 8 feet tall, barely anybody is that tall. Similarly, barely anybody is like 4 feet tall as well. So the most popular values are in the middle, and it gets decreasingly popular as you go to either side. So the mean of a normal distribution is found dead middle because it is a balancing point here. So I'm going to go ahead and put 149 right there in the middle. And the standard deviation, we've learned that means your typical distance from the mean. In the context of a normal curve problem, the standard deviation is the amount that our tick marks go by that we care about. It breaks our graph up into chunks, and we do 3 tick marks in each direction from our center. The first chunk should happen somewhere around the inflection point. So I'm going to be like somewhere in this area right here where it switches from down to up. So maybe like there, for example. That's 1 standard deviation away from the center to the inflection point-ish. And then I'm going to try to keep my sections the same width right here. And I'm going to break it up 3 times in each direction. So all of these pieces should be the same width because we're counting by the same standard deviation, which in this problem is 9. So each of my tick marks goes 9, like this plus 9, etc. This should, again, look familiar to you guys. So go ahead and fill this out, and I will do so on my paper as well. So we have our little picture filled out right here, and these are going to be the heights that we care about. The heights that are either 1 standard deviation, 2, or 3 away from our mean. And as you might remember from Algebra 2, what we really care about when we do these is what percent of values live in each section of this graph. So what percent of 12-year-olds are between 140 and 149, or 158 and 176, or whatever. So I'm going to come back to this, and I don't want to delete it yet, but I'm just going to click ahead here. When I click ahead on these, this is for an investigation where we'll talk about the percentages. We'll do that later on in class, or we've already done it by the time you've watched this, I don't know. So I'm not going to talk about this slide, but I am going to go ahead and move to this slide right here. So on this slide, I have the famous rule that you guys do have to have memorized, and it's called the 68, 95, 99.7 rule. And that tells you what percent of values fall within 1, 2, or 3 standard deviations of the mean. So that's all written right here, and you can see approximately 68% of observations fall within, this is just sigma, standard deviation. So 1 standard deviation of the mean, 2 standard deviations of the mean, and 3. And it's got the percents labeled in this picture, but I didn't want to erase mine right here because we're going to need it in just a second. At the bottom here, though, you guys will be able to see this better on your slides than you can on my picture right here. But you'll see that the values go from 0 and then 1, 2, and 3 standard deviations away. Those are z-scores, because z-scores count how many standard deviations you are from the mean. If you're 0 standard deviations from the mean, you are the mean. You're in the middle right there. You're 1 standard deviation away, 2, or 3. So your x-axis right here on this picture is actually going to be your z-score, how many standard deviations away you are. So we're going to use this picture, and we're going to figure out a couple of probabilities here. What percent of 12-year-olds will be over 158 tall? So I'm going to tab back to where I had more space. And I'm going to show you guys, again, you've done this in Algebra 2, but you'll see how to get your percentages. Within 1 standard deviation of the mean is 68% of your data. So I'm going to take 68% and I'm going to divide it into 2 even parts for right here and here. Each of these sections is going to be 34% of your data. That's 68 divided by 2. 2 standard deviations away is 95% of your data. So I do the same sort of concept here, but I've used up 68 of it already. So I would take 95 and I would subtract 68. There's going to be 27 left over. And then I would do 27 divided by 2, Each of those next sections are 13.5. So 13.5. And if you follow the same process, you do your 99.7, subtract, blah, blah, blah. What you're going to end up finding is that it goes 2.35%. And that's 99.7% of your data. The last parts on the end are not even 1%. They're 0.15%. So if you guys recall, the question that we cared about asked what percent of males are 158 or above. Well, 158 is going to be this mark right here in green. Everybody above 158 is going to be these parts. So you're just going to add those up and you're going to get your answer for the problem. Alternatively, you could go ahead and subtract out all the ones you don't want. I know that's going to be 50 for the whole left half, and then another 34 is 84. So that's 16% for these ones right here. So that problem, which asked about the over 158, it's going to be about 16% of 12-year-olds that will have that height. So let me tab back ahead and figure out what the next question says. It says between a 131, and I think that says 140. Yeah, so 131 and 140 were my numbers for the next problem. And these, again, not terribly bad. All I'm going to do is the same sort of concept right here. I just totally erased the one number that I actually needed. But if I have 131 to 140, that's going to be this box right here. This box is a 13.5%. So doing these questions here is not very bad. Again, you guys learned how to do them in Algebra 2 with me, so it couldn't have been anything too crazy. So let's keep it going here. There are different styles of question I could ask you with the same setup, like using the same concept, but in a different way. So this time they say the middle 95% of scores are between 72 and 84. So what I would do with that is I would make sure when I draw my picture right here, the middle 95% means 2 standard deviations. So it's going to be this mark, and it's going to be this mark right here. That's 95%. And it says those are between 72 and 84. And then they're going to ask us what the mean and standard deviation are. The whole key to this is that the problem is symmetric. So what we can do is we can just find the average of those two, and that would get us the mean right here. Halfway in between those two values is a 78. And then I can do the same process again. This would be a 75. This would be an 81. So what is the mean? Well, the mean of this problem is the middle, which is the 78. And the standard deviation is how much each tick mark goes by, and we're going by 3s for this problem. So I'm going a little faster through this because you've seen it before, but I want to kind of plant a seed right here with this last question. I believe this is the last question. Let me make sure I don't have another slide. Yeah, this is it. So the issue with what we learned and with that rule that we just covered, 68, 95, 99.7, it only works for specialized values where it lands exactly on one of these tick marks right here. If I ask you for the percent of scores that are above 80, 80 is somewhere like here. Well, I could get fairly close to the answer just by the percentages I do know. Like if I took these last parts right here, I could add this part, this part, this part together and try to eyeball this right here and get fairly close to the answer. But in actuality, that rule is just like an easy guideline that we teach kids first, just to give you a basic sense of what's going on. There is a more sophisticated way that we can find the exact area for any value that I wanted that's not just one of my tick marks right here. So we will learn how to do this, but we're going to learn it in our next lesson.